The space between galaxies is not empty. It only feels that way because our senses were shaped on a warm, dense world, not in the quiet cold between the stars. Out there, in the vast reaches of intergalactic space, matter thins to almost nothing. Atoms drifting for millions of kilometers before meeting a partner, light traveling for billions of years without touching dust, gravity stretching until it becomes little more than a suggestion. It is a region so silent, so sparse, that the universe itself seems to fade into a kind of cosmic hush. And yet, this near nothingness is part of everything. It shapes galaxies, bends their motion, slows their collisions, and traces the large-scale architecture of the cosmos. The voids between galaxies are not empty gaps, but structures, vast, ancient, and essential. If this quiet journey brings you even a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps this small corner of the universe keep glowing, and I hold your presence with real gratitude. Now we drift into Part 1. Part 1. What actually fills the space between galaxies? Between the great continents of galaxies lies a darkness so thin it defies intuition. Yet, it is not true emptiness. The intergalactic medium, made of lone atoms, wandering ions, faint radiation, and elusive particles, drifts like an almost invisible fog stretching across hundreds of millions of light years. To understand the cosmic void, we must begin with this sparse but essential substance. Imagine drifting outward from a familiar spiral galaxy, past its bright core, past its outer halo, until even the last faint orbiting stars fall behind you. Beyond them, the starlight dims into a soft blur. Then, the blur becomes a faint mist. And finally, the mist dissolves into something that feels like nothing at all. This is the boundary where the galaxy ends and the intergalactic medium begins. A threshold so subtle there's no line to cross, only a gradual fading. Yet, despite its silence, this space contains the faint ingredients of the universe's earliest chemistry. Even here, far beyond the gravitational arms of galaxies, tiny particles drift. A hydrogen atom might spend 1,000 years without meeting another. A lone helium nucleus may travel across tens of thousands of kilometers without disturbance. These particles are scattered at densities so low that a cubic meter of this space might contain only a few atoms. On Earth, by comparison, the air you breathe contains trillions upon trillions of particles in every breath. The contrast is almost beyond imagination. And yet, the intergalactic medium is vast enough that, collectively, its particles account for a significant fraction of all normal matter in the universe. You can think of this medium as a quiet archive of cosmic history. Most of its atoms were forged in the first minutes after the Big Bang, remnants of the primordial fireball still drifting through the universe, nearly unchanged. Hydrogen, the simplest and most abundant element, dominates this endless expanse. Where hydrogen goes, the universe follows. Its distribution, its clumps, its rarefied streams, they trace the architecture of the cosmic web. But these atoms are not always neutral or calm. In many regions, the intergalactic medium exists in a state of ionization. Stripped of their electrons by early generations of stars, many hydrogen and helium atoms wander as charged particles. These ions respond to faint magnetic fields and carry clues about the radiation that once illuminated the universe. We often think of emptiness as a lack of energy. But here in the void, there's a subtle hum, a relic whisper from the first stars, the first quasars, and the earliest bursts of cosmic light. If you could watch the intergalactic medium over millions of years, you would see it flow and stretch like a vast invisible tide. The gravity of massive clusters pulls some of it inward, feeding galaxies with fresh gas. Other regions expand and empty out, creating cosmic deserts, voids where matter is so scarce that light can travel unimpeded for half the age of the universe. Though it moves slowly, this medium is constantly reshaping itself, evolving with the grand architecture of the cosmos. And yet, for all its vastness, much of the intergalactic medium remains hidden from our eyes. Its atoms are too far apart to glow visibly. Its ions emit only faint signatures detectable with sensitive telescopes tuned to the ultraviolet or X-ray wavelengths. When scientists search for it, they often look not at the medium directly, but at what it does to light that passes through it. A distant quasar shining from billions of years away has its light subtly altered by the clouds of intergalactic gas it travels through. Each cloud leaves a tiny fingerprint, absorption lines etched into the quasar's light like whispers from across the ages. These fingerprints reveal something remarkable. The intergalactic medium is not evenly spread. It pools into filaments hundreds of millions of light years long, forming the connective tissue between clusters of galaxies. Along these filaments, gravity has drawn matter together into tenuous rivers, shaping the universe into a structure that resembles a cosmic web. Between the filaments lie immense voids, regions so empty that they challenge the very meaning of space. Still, even the emptiest parts of these voids are not completely barren. A few lonely particles drift through them, carrying faint traces of cosmic evolution. There are stray photons from the cosmic microwave background, the afterglow of the Big Bang, passing through unchallenged. These photons are everywhere, filling every cubic centimeter of space, forming a soft bath of ancient light that permeates even the deepest voids. They do not illuminate the darkness, but they quietly warm it, a subtle imprint from a time when the universe was young and hot. There are also cosmic rays, high-energy particles accelerated by violent cosmic events. They streak across the void at nearly the speed of light, unimpeded by dust or gas. In the crowded interior of a galaxy, these particles might be absorbed, scattered, or slowed. But in the intergalactic medium, they travel freely, carrying with them the signatures of supernovae, black holes, and star-forming galaxies. Each one is a traveler from a distant past, crossing the universe in silence. The intergalactic medium also contains something stranger, something we cannot see or touch. Dark matter threads through this region, forming invisible scaffolding that shapes the flow of ordinary matter. Without dark matter, the intergalactic medium would drift too freely to form the rich structures we observe. Its gravity subtly sculpts the cosmic web, guiding gas toward filaments and clusters and deepening the great voids in between. Though dark matter does not shine, does not collide, and does not slow down, its presence defines the landscape in which the intergalactic medium moves. In some regions, the medium is warmed by powerful cosmic engines. Quasars, supermassive black holes at the centers of distant galaxies, emit enormous amounts of energy, heating nearby gas to millions of degrees. This hot gas emits X-rays, lighting up the darkness with faint but detectable glow. In other regions, the medium remains cold and thin, drifting without disturbance for billions of years. It is a patchwork of temperatures, densities, and histories, all woven together by the quiet laws of physics. If you could wander through this space, you would not hear anything. With so few particles, sound cannot travel. There is nothing to carry the vibration of a wave. Even time feels different here, stretched by cosmic expansion and shaped by the faint pull of distant galaxies. But silence does not mean stillness. The intergalactic medium flows, evolves, and participates in the slow choreography of the universe. As the universe continues to expand, this medium thins further. Galaxies draw from it less frequently. Voids widen, filaments stretch. In the far future, the intergalactic medium may become even more diffuse, growing colder as the universe ages. But for now, it remains the quiet ocean between the islands of galaxies, holding the history of the cosmos in its barely there currents. And as we drift deeper into this quiet expanse, one question remains. If the space between galaxies is filled with something, then why does the universe still look so astonishingly empty? Part 2. Why the universe has vast web-like voids. If you could rise far enough above the cosmos, the universe would look like a glowing web, filaments of galaxies outlining enormous cavities of nearly perfect nothingness. These voids didn't appear randomly, they emerged from tiny fluctuations in the early universe. As gravity gathered matter into clusters, the empty regions between them grew, leaving behind some of the largest structures ever discovered. To understand why these colossal gaps exist, we have to imagine the universe as it once was: hot, dense, fluid, and almost perfectly uniform. In those first few 100,000 years after the Big Bang, matter was spread so evenly that, from any vantage point, everything looked the same. There were no galaxies, no stars, no dark spaces, just a smooth sea of particles and radiation. And yet, hidden in that uniformity were tiny imperfections, minute variations in density, no larger than differences in temperature of a few millionths of a degree. These tiny ripples are where the entire structure of the modern universe began. Imagine the early universe as a vast ocean, and these fluctuations as barely perceptible waves on its surface. The denser regions were ever so slightly more massive, giving them a slightly stronger gravitational pull. Over immense stretches of cosmic time, these tiny differences were amplified. Gravity gathered matter into the denser areas, while the less dense regions emptied further. It is a simple rule: where matter collects, more matter follows, and where matter departs, emptiness deepens. This process unfolded slowly at first. After all, gravity is gentle across large scales. But as billions of years passed, the slight variations in density grew into clear patterns. Dense regions collapsed into stars, galaxies, and clusters. Sparse regions expanded into vast voids, and the cosmic web began to emerge, filaments stretching across the universe like the strands of a living, breathing organism. The result is something both beautiful and humbling. The largest structures in the universe are not the galaxies themselves, but the empty spaces between them. These voids can span hundreds of millions of light years across, dwarfing even the most massive galaxy clusters. A single void is so large that the entire Andromeda galaxy, home to 1 trillion stars, could drift through it without touching anything. These regions are not just empty, but profoundly empty. Some contain only a handful of galaxies in volumes where one might expect thousands. But emptiness is not an absence of cause. It is a consequence of the universe's earliest laws. The cosmic microwave background, the faint relic glow of the Big Bang, carries within it the imprint of those original fluctuations. When scientists map this ancient radiation, they see patterns, warmer spots and cooler spots, each representing slightly different densities of early matter. These subtle patches form the blueprint from which the entire cosmic web evolved. Every void and filament we see today can trace its ancestry back to these initial flickers in the young universe. As the universe expanded, these patterns stretched. The denser regions grew heavier, attracting more matter and sharpening the contrast between full and empty. Dark matter played a crucial role in this development. Though invisible, dark matter formed the underlying scaffolding of the cosmic web. It clumped in the denser regions, creating gravitational wells that ordinary matter, gas, dust, and later stars, fell into. The voids, by contrast, became places where dark matter was sparse. Without dark matter to anchor it, ordinary matter simply moved away, deepening the emptiness. This is why the universe looks like a web rather than a random scattering of galaxies. Gravity is not distributed evenly. It pulls more strongly in some places than in others. Over billions of years, matter flows along these gravitational gradients, collecting in long, thread-like filaments that connect massive clusters like cosmic highways. The spaces between these highways become regions of desert-like isolation. If you could float within a void, the experience would be surreal. You might travel for tens of millions of years before encountering a single galaxy. The night sky, if viewed from a lone planet there, would be sparsely populated. Instead of the dense tapestries of stars we see from Earth, you would see only a few faint glimmers. It would feel like standing inside a cathedral of darkness where space itself seems to stretch without resistance. Yet despite their emptiness, voids are not irrelevant. They play a critical role in shaping the universe. Much like valleys between mountain ranges, voids define the contours of the cosmic landscape. By expanding more rapidly than surrounding regions, voids help push matter into filaments and clusters, amplifying the structure of the cosmic web. In essence, the emptiness helps shape the fullness. Without voids, the universe would have no large-scale structure, no filaments, no clusters, no galaxies arranged in graceful interconnected networks. Over time, voids themselves evolve. As the universe expands, the emptiest regions stretch faster than others. Dark energy, the mysterious force accelerating cosmic expansion, acts even more strongly in regions where matter is scarce. With fewer gravitational anchors, voids balloon outward, growing larger and emptier with every passing epoch. This means that the cosmic web becomes more exaggerated. Galaxies cluster more tightly along filaments, while voids widen into vast cosmic oceans. It may seem counterintuitive, but studying voids reveals some of the universe's deepest secrets. Cosmologists examine how voids expand to probe the nature of dark energy. They analyze the few galaxies trapped within voids to understand how isolation affects star formation and evolution. They even map the shapes of voids to test fundamental physics, because distortions in their geometry can reveal the presence of unseen forces or exotic forms of matter. Voids also offer a unique environment for observing the universe's large-scale behavior. With so little matter inside them, they act like cosmic laboratories where gravitational influences from surrounding clusters become easier to measure. Galaxies in voids move differently from galaxies in crowded regions. Their paths trace the faint whisper of the universe's overall structure rather than the tangled local motions inside clusters. In the deepest voids, temperature behaves oddly. Because particles are so scarce, heat cannot spread. A single ion might carry energy for thousands of years without sharing it. Radiation travels freely. Cosmic rays speed through unimpeded, and the cosmic microwave background drifts through these chambers without any significant scattering, making voids some of the cleanest windows into the early universe. Perhaps the most fascinating feature of voids is their scale. Some span hundreds of millions of light years, so large that light takes longer to cross them than complex life has existed on Earth. Others are smaller, nested within larger voids like pockets inside pockets. The cosmic web is fractal-like, repeating patterns on different scales, each shaped by the same simple laws of gravity and expansion. And yet, as vast as these voids are, they tell a story of delicate beginnings. The entire architecture of the cosmos, from the richest galaxy cluster to the most silent void, emerged from fluctuations so small they could barely be measured. The universe did not begin with order. It began with randomness, smoothed by time, shaped by expansion, and sculpted by gravity. As we drift deeper into this gentle puzzle, one quiet question rises. If these voids define the shape of the universe, what do they reveal about the forces that continue to pull everything apart? Part 3. How empty is empty? On Earth, emptiness is air. In space, emptiness is vacuum. But in the void between galaxies, emptiness becomes something stranger, density so low that a single proton might drift for miles without meeting another. Here, silence takes on a physical meaning defined by absence itself. Understanding the scale of emptiness requires letting go of every instinct we evolved to survive on a dense planet. To grasp what empty really means in intergalactic space, we first have to understand what our senses were built for. Every moment of your life, you've breathed through an ocean of molecules so thick that each cubic millimeter of air contains billions of particles. Your skin feels pressure because countless atoms collide with it every second. Sound reaches your ears because molecules bump and vibrate in shifting waves. Everything you've ever touched, heard, smelled, or breathed comes from a world where matter is plentiful. Even the emptiest places on Earth, high mountaintops, sealed vacuum chambers, dry desert air, remain impossibly dense compared to space. In a vacuum chamber pumped down until nearly all air is removed, you still have about 10 million particles per cubic centimeter. That is already billions of times emptier than the air we breathe. But it is still crowded compared to interstellar space, and interstellar space in turn is crowded compared to the voids between galaxies. In the regions between stars within a galaxy, Densities drop to just a few atoms per cubic centimeter. That may sound empty, and by human standards it is. But in the cosmic voids, those vast spaces that stretch between galaxy clusters, the density can be less than one atom in an entire cubic meter. And some regions of the largest voids may fall to even lower densities. One proton for tens of cubic meters, or maybe one lonely atom in the volume of a house. It is an emptiness so profound that it becomes almost philosophical, a kind of physical silence. When matter becomes this sparse, all the behaviors we associate with particles change. There is no pressure, no sound, no wind, no collisions. A proton could drift for thousands of years without touching anything. An electron might wander for light years before encountering a lone photon. Even light behaves differently. In crowded regions, photons bounce, scatter, absorb, blur. But here, light streams freely, unchanged over billions of years, carrying ancient stories from galaxies long gone. This absence is not just the lack of atoms, it is the lack of interaction. On Earth, matter is always interacting. Particles collide constantly, exchange energy, release heat, vibrate, glow. In a cosmic void, the opposite happens. Particles exist, but they almost never meet. Energy cannot spread. A warm particle stays warm for a long time. A fast particle stays fast. Nothing bumps into it to share momentum or pull it toward stillness. Temperature, in this strange environment, becomes almost meaningless. Temperature on Earth is a measure of how often particles collide and how much energy they exchange. But in the cosmic void, there is almost nothing to exchange. If you could somehow place a thermometer there, it would read a temperature close to absolute zero, not because particles aren't moving, but because there are almost none to measure. Temperature becomes an abstraction, a mathematical reflection of average energy rather than something you could feel. This extreme emptiness also changes how time is experienced. Not time in the human sense, but time as physicists describe it, the relationship between motion, energy, and interaction. In dense environments, reactions occur rapidly. Atoms combine, molecules vibrate, photons scatter. But in the void, the universe slows down. Chemical reactions become impossible. Cooling takes eons. Change stretches across cosmic timescales. A cloud of gas might drift unchanged for billions of years, simply because nothing touches it. Yet even here, emptiness is not complete. There is no such thing as absolute nothingness in the universe. Even the darkest void contains the relic light from the Big Bang, the cosmic microwave background. These ancient photons permeate every corner of existence, filling the emptiest void with a faint whisper of radiation just a few degrees above absolute zero. Though they barely interact with matter, they provide a subtle background glow, a kind of ghostly presence in the darkness. There are also cosmic rays, high-energy particles launched by supernovae, black holes, and violent cosmic events. They race through the void almost entirely unhindered. In a galaxy, magnetic fields and gas clouds might deflect or absorb them, but in intergalactic space, they move freely. Some have been traveling for billions of years, carrying the imprint of ancient explosions across unfathomable distances. They are messengers of the universe's most extreme events, traveling through the quietest environments imaginable. Dark matter, too, threads through the void. Though invisible and undetectable except through its gravity, it exists everywhere, even in regions devoid of normal matter. In the largest voids, dark matter density is lower than average, but never zero. Its presence shapes the motion of galaxies around the void's edges and influences how the void expands. It is part of the cosmic framework, the unseen structure beneath the visible universe. This raises an intriguing truth. The void is not truly empty, but it is empty enough that the rules of nature soften. Forces that dominate our daily lives barely operate here. Gravity still acts, but so faintly that its pull accumulates only over millions of years. Electromagnetic interactions, so strong in dense environments, become occasional curiosities, rare events separated by light years. If you placed a charged particle in the center of a void, It might take longer than the age of the universe to find another with which to interact. Even space itself behaves differently in these regions. The expansion of the universe plays a larger role here than in denser areas. With little matter to slow it, space expands more freely, stretching distances between the sparse particles even further. It is as if the universe breathes more deeply in these places, inhaling emptiness and exhaling space. In such an environment, the concept of isolation takes on an entirely new meaning. A lone galaxy drifting inside a void might be tens of millions of light-years away from its nearest neighbor. Its stars would form more slowly, its gas would remain undisturbed, its evolution would be shaped not by interactions, but by solitude. The galaxy might look fragile, faint, and blue, forming stars at a whispering pace. In crowded clusters, galaxies grow through collisions. In voids, they grow through patience. If you stood somehow in the heart of one of these voids, on a hypothetical world warmed by its own faint internal processes, you would see almost nothing in the sky. A few dim galaxies might dot the darkness. The Milky Way would be invisible, just one distant speck among many. With so few stars above you, night would feel endless. Time would feel endless. Space would feel endless. And the silence would not just surround you, it would define you. There is something humbling about this. Our instincts tell us that empty space should feel cold, lifeless, boring. But the cosmic void is anything but. It is a frontier where the laws of physics slow down, where the universe's structure becomes clearer, and where the faintest particles carry vast, unbroken histories. It is a reminder that the universe is not built from fullness alone. It is built from contrast, clusters and voids, matter and absence, light and darkness. And yet, in contemplating this profound emptiness, another question gently rises. If even the emptiest regions of the universe still contain something, then does true emptiness, absolute nothingness, exist anywhere at all? Part 4. Why temperature behaves differently in the cosmic void. In intergalactic space, temperature becomes a quiet paradox. The few particles that exist move with incredible speed, yet their sparseness makes the void feel unimaginably cold. Heat cannot spread, and energy cannot easily collide. The result is a region where temperature has meaning only when traced through motion, not through touch. To understand why temperature behaves so differently here, we first need to revisit what temperature actually means. On Earth, temperature is intuitive. It's the warmth of sunlight on your skin, the bite of winter air, the steam rising from a cup of tea. It feels immediate and physical because air is dense, full of molecules that constantly crash into you, transferring energy through each collision. We experience temperature through contact, through the steady exchange of energy between our skin and the world around it. But temperature itself is not a sensation. It is a measure of average energy, the average speed of particles bouncing, vibrating, colliding. In dense environments like Earth's atmosphere, those interactions are constant. Billions of collisions occur every second, giving temperature its tangible quality. But once you leave the Earth, once you leave a galaxy entirely, temperature becomes something quieter, something almost abstract. In the cosmic void, there are so few particles that collisions are rare events. A single proton may travel for years without hitting another. An electron might drift unimpeded for thousands of kilometers. Without collisions, heat cannot spread. There's no medium for warmth to move through. If you placed a warm object in the void, it would not feel warm or cold against the space around it. Its heat would simply radiate away as infrared light, slowly fading into the cosmic background. There is no air to warm, no molecules to vibrate, no medium to carry sensation. This leads to one of the strangest truths in astrophysics. The void can contain particles moving at millions of kilometers per hour and still behave like a place only a fraction of a degree above absolute zero. It's a paradox created by scarcity. Fast-moving particles have high kinetic energy, which implies high temperature. Yet because there are so few of them, that temperature cannot be felt. It exists only on paper, defined statistically. The void feels cold not because its particles are slow, but because they are few. Consider an analogy. A single spark in a dark field can be incredibly hot, but it cannot warm the field around it. There simply isn't enough fire to do anything. The cosmic void is like that field. A lone particle may be energetic, but it cannot share that energy with anything else. This strange, almost philosophical definition of temperature leads to even stranger consequences. For instance, in the void, objects don't cool quickly in the way they would on Earth. A warm object on Earth loses heat rapidly to the air around it. But in the void, the only way to lose heat is for the object to emit radiation, photon by photon, into empty space. That process is slow. A spacecraft drifting far from any star does not freeze instantly. Instead, it cools gently over long periods, its warmth bleeding away like a whisper fading in an empty cathedral. Even more surprising, objects do not heat up quickly either. If one energetic particle strikes another, the transfer of heat is real. But because collisions are rare, heating is an almost glacial process. A gas cloud in the void might require millions of years to warm significantly from absorbed starlight or cosmic rays. This interplay between warmth and emptiness makes the void one of the most thermally stable environments in the universe. Large temperature swings do not occur suddenly. Energy changes happen only slowly, guided by expansion, radiation, and the rare collision of particles. This stability is why the cosmic microwave background radiation, just 2.7 degrees above absolute zero, permeates the universe so evenly. The void provides an environment where energy cannot easily bunch up or clump. Radiation has traveled freely across billions of years, smoothing itself across all of space. Without matter to interrupt it, the microwave background becomes one of the most uniform fields ever observed. It cools steadily as the universe expands, but its distribution remains astonishingly consistent. The cosmic void also gives scientists a laboratory to study low-density physics, conditions impossible to recreate on Earth. Because collisions are so infrequent, particles behave independently, following pure trajectories. Their temperatures reflect individual histories rather than collective behavior. A single proton might be heated by a cosmic ray, accelerated by magnetic fields, or chilled by expansion. In dense environments, particles quickly share energy, smoothing out differences. But in the void, every particle carries its own story, its own thermal memory. This independence leads to another paradox. If you could place a thermometer into the void, what would it read? The answer depends entirely on the thermometer. A thermometer that measures particle collisions, like the ones we use on Earth, would register a temperature near absolute zero because hardly anything hits it. But a thermometer designed to measure radiation would detect the cosmic microwave background's temperature. A thermometer that senses individual particle speeds might record wildly different values depending on which particle it encounters. In the void, temperature is less a physical experience and more a question of perspective. Even gravity contributes to the thermal behavior of these regions. As voids expand faster than surrounding areas, any gas drifting near their centers becomes stretched, cooled, and rarefied. This process, called adiabatic cooling, is similar to air expanding and cooling in Earth's atmosphere, but on a scale of hundreds of millions of light years. The void itself becomes a kind of enormous cosmic refrigerator, deepening its own chill as it grows. Yet the void is not entirely passive. At its edges, where filaments of matter concentrate, temperatures can rise sharply. Gas squeezed into filaments can heat to millions of degrees, energized by falling into gravitational wells. These hot regions remain fundamentally separated from the center of voids because energy simply cannot travel inward. Temperature contrasts that would equalize quickly on Earth remain stable for billions of years in space. This thermal isolation explains why galaxies inside voids tend to look different from their crowded cousins. In dense environments, galaxies feel the heat of nearby structures, radiation from quasars, shock waves from collisions, winds from neighboring galaxies. But in a void, a galaxy lives in quiet thermal solitude. It evolves more slowly. Its gas remains cooler. Star formation trickles rather than bursts. The galaxy's temperature history becomes as gentle as the void itself. And beneath all of this, something even more subtle operates: the universe's expansion. As space itself stretches, photons lose energy. Their wavelengths lengthen, shifting from visible light to infrared to microwave. The universe cools not because heat escapes, but because space expands around the energy that exists. In the deepest voids, where nothing interrupts this stretching, cooling becomes even more efficient. These regions feel like the universe's natural resting state: quiet, cold, and patient. The cosmic void reminds us that temperature is not a simple measure of heat, but a dance between motion, density, and interaction. It shows us that warmth is not just the speed of particles, but the ability to share energy. In the void, sharing becomes rare, and so temperature becomes something solitary, felt only by the particles themselves. And as we drift through this paradox of hot particles and cold space, another quiet question emerges. If the void makes heat so difficult to spread, how does light itself travel so effortlessly through such profound emptiness? Part 5. The strange orbits of galaxies. Surrounded by nothing, gravity behaves differently when a galaxy is isolated in emptiness. With little external matter to tug on it, a galaxy drifts through the void like a lantern in a vast, silent sea. Its motion is shaped not only by its own mass, but by the faint pull of distant clusters and the hidden threads of dark matter that extend far beyond the stars we can see. To understand a galaxy's orbit inside a cosmic void, we first need to imagine what it means to be alone on such a monumental scale. On Earth, isolation is measured in miles. Even in deep space, isolation is measured in light hours or light days. But in a cosmic void, isolation becomes something far larger. Tens of millions of light years of silence surrounding a single galaxy, like a hollow spherical cathedral. There are no nearby companions to disturb its path, no packed clusters to stir its gravity, no violent mergers to reshape its structure. Just a lone island of stars adrift in darkness. In such an environment, a galaxy behaves differently from its cousins in crowded neighborhoods. Inside clusters, galaxies orbit chaotically around a shared center of mass. They tug on one another, fall inward, collide, distort. But in a void, a galaxy has no such company. Instead, it moves gently, almost languidly, responding only to subtle gravitational gradients that stretch across unimaginably large distances. Its orbit is not a loop around a local center, but a slow drift through expanded space. This drift is shaped first by the galaxy's own weight. Every spiral or elliptical galaxy sits inside a dark matter halo, an invisible sphere of mass that far outweighs the stars, gas, and planets within it. The halo determines how a galaxy rotates internally and how it interacts externally. In dense environments, halos overlap and collide, but in voids, a halo can float freely, unperturbed. This freedom means a void galaxy retains a pristine structure, its rotation curve stable, its shape unwarped by tidal forces. Yet even isolation does not mean stillness. Gravity carries its influence across infinite distances, weakening with space but never reaching zero. A lone galaxy still feels the pull of distant clusters, superclusters, and the overarching structure of the cosmic web. These pulls are faint, so faint that their effects accumulate only across billions of years, but they shape the galaxy's trajectory. Its movement is a slow, patient response to the geometry of the universe. To visualize this, imagine a ship drifting in a vast ocean where the currents are almost imperceptible. The ship may seem still, yet over time, it drifts along pathways carved by forces it cannot feel moment to moment. The galaxy behaves the same way. Its motion through the void follows a long, curved path guided by the invisible pull of distant masses. One of the most surprising aspects of void galaxies is that they often move faster than expected. With little friction, no dense gas, no nearby galaxies, their motion through space is less hindered. They move as though slipping across a polished floor, maintaining momentum across cosmic distances. Some void galaxies display unusually high peculiar velocities, speeds that differ significantly from the general flow of cosmic expansion. suggesting they've been accelerated by gravitational interactions long past. These motions reveal the hidden structure of the universe. When astronomers map the trajectories of void galaxies, they can trace subtle forces at play, like faint outlines of a painting revealed by dust. A void galaxy's orbit can indicate the presence of a distant supercluster, or the position of a massive filament, or even the influence of dark matter that cannot be detected directly. Each galaxy becomes a probe of the cosmic landscape, its path shaped by the invisible skeleton beneath. Inside the void itself, motion feels different. Because matter is so sparse, the usual markers of velocity vanish. There is no dust to heat, no gas to shock, no neighbors to disturb. A galaxy could travel at hundreds of kilometers per second without producing any visible trail or disturbance. Its stars continue their internal dance, rotating around the galaxy's center, but the galaxy's movement through the void is silent, smooth, and almost ghost-like. Dark matter plays an essential role here. While ordinary matter gathers into stars and gas clouds, dark matter forms a more extended diffuse halo around each galaxy. The halo can stretch far beyond the visible boundary of the galaxy, blending subtly into the surrounding void. It is the dark matter halo that interacts gravitationally with the large-scale cosmic web, serving as the galaxy's anchor to the broader universe. Without this halo, a galaxy in a void might behave much more unpredictably, its motion less stable. And yet, despite their isolation, void galaxies are remarkably resilient. Without the disruptive interactions common in clusters, ram pressure stripping, tidal forces, galaxy harassment, they maintain their gas reservoirs longer. Many continue forming stars at a slow but steady pace, drawing from ancient supplies of cold gas preserved by their solitude. Some display unusually pristine chemical compositions containing higher fractions of primordial elements left almost untouched since the early universe. This slow, gentle evolution affects their orbits as well. A void galaxy does not gain mass rapidly from mergers because mergers are exceedingly rare in such regions. With less mass growth, its motion remains steady, dictated by long-range gravitational fields rather than sudden jumps. It becomes a traveler with a consistent speed, guided by the faint pull of the cosmic web's distant peaks and valleys. The most intriguing aspect of these orbits is how they relate to the expansion of the universe. Everywhere in space, galaxies move apart due to cosmic expansion, but in voids, where gravity is weakest, this expansion dominates even more strongly. A void galaxy is carried outward by the expansion of space faster than galaxies in dense regions. It is as if the void stretches space beneath it like a slow, widening tide, pushing it gently outward. This creates an effect where void galaxies appear to accelerate away from denser regions, exaggerating their motion compared to the rest of the cosmic web. Over billions of years, this motion amplifies the void's emptiness. Galaxies drift toward filaments, leaving the void center even more vacant. The few that remain may travel along long, gentle arcs that emphasize the void's shape, curved paths that reveal gravitational gradients too subtle to detect in any other environment. If you could watch a void galaxy over billions of years, you would see it move almost like a leaf drifting in a slow breeze. No crashes, no violent encounters, just a long, patient glide through expanding space. Its orbit would not be a closed loop like planets orbiting a star, but a wandering trajectory shaped by the changing universe around it, by the growth of voids, the pull of distant clusters, and the shifting geometry of space-time. This gentle drift offers a profound perspective on gravity. It reminds us that gravity is not always a dramatic force. Sometimes it is a whisper, an ever-present guidance that shapes motion without sound or spectacle. In voids especially, gravity becomes almost philosophical, a force that directs without touching, shaping the path of galaxies through emptiness. As we continue to explore this quiet motion, another question begins to rise like a soft tide. If galaxies move so freely through the void, what happens to the light they emit as it travels across these vast, empty expanses? Part 6. Why light travels differently through the void. A photon leaving a distant galaxy enters a realm where nothing stands in its way. Here, light can cross billions of years without interruption, carrying ancient stories from the early universe. The void does not distort it, dim it, or scatter it, yet cosmic expansion gently stretches each wavelength as if the universe itself were breathing around it. To understand why light behaves so uniquely in the cosmic void, we need to first recall how light interacts with matter. On Earth, light rarely travels freely. It collides with atoms in the air, scatters off dust, refracts through glass, or absorbs into surfaces. Even in the vacuum we can create in a laboratory, residual molecules remain, enough to make light deviate slightly from a perfectly straight, uninterrupted path. Inside a galaxy, the situation is no different. Dust clouds obscure starlight, gas absorbs specific wavelengths, magnetic fields twist and polarize photons. Light is constantly interacting, constantly being reshaped by the environment through which it moves. It is a messenger, yes, but often a messenger bruised by its journey. But when a photon leaves the structured interior of a galaxy and drifts into the vast emptiness between galaxies, the rules begin to change. In these regions, the density of matter becomes so low that a photon could travel for millions of years without encountering a single particle. There is nothing to scatter off, nothing to absorb it, nothing to slow it, nothing to bend its path, except the broad curvature of space-time itself. This near-perfect freedom gives the void a unique property. It becomes the closest approximation to a pure vacuum that exists in nature. And in that purity, light reveals its truest behavior. In dense regions, photons scatter and lose direction, but in the void, a photon's direction remains astoundingly faithful to its origin. When astronomers observe distant galaxies, the reason those images arrive crisp and coherent is because their light has spent most of its journey traveling through voids. These empty spaces protect light from the noise of the universe, like a sound carried clearly through still winter air. Yet emptiness is not the only force shaping that journey. As the photon travels, the universe continues to expand. Space is stretching, not dramatically in local terms, but steadily and relentlessly across cosmic scales. And because light travels through space, not through a medium, its wavelength stretches along with the fabric it crosses. This stretching is known as cosmological redshift, and it is one of the most profound consequences of the expanding universe. Imagine marking 2 points on a rubber band and then stretching it. The distance between the marks increases, and if a wave were drawn between them, its crests would spread apart. The same happens to light. Its color shifts toward the red end of the spectrum. Its energy decreases, even though nothing touches it. Light ages as it travels, not because of friction or obstruction, but because space itself expands beneath it. This effect is one reason why galaxies billions of light years away appear redder than they truly are. Their galaxies aren't emitting red light, they're emitting normal starlight. But by the time that light reaches us, its wavelengths have been stretched, sometimes dramatically. In the deepest cosmic voids, where nothing interferes with the expansion of space, this redshift becomes a clear and uninterrupted measure of cosmic history. But redshift is only one part of the story. Light experiences another shift when it travels near massive objects. In galaxy clusters, photons can lose energy climbing out of gravitational wells, a process called gravitational redshift. But in the void, where gravity is weak, photons travel almost unburdened. They lose no additional energy to local distortions of space-time. Their only change comes from the gentle universal stretching of the cosmos. This means that photons traveling through voids hold some of the most pristine information in the universe. They carry the cosmic microwave background, light from when the universe was only 380,000 years old, across nearly empty space, preserving its delicate fluctuations with astonishing fidelity. Without the void, the image of the early universe we have today would be blurred, noisy, mottled by constant interference. Instead, it is clear enough for cosmologists to measure temperature variations only millionths of a degree apart. The void acts like a corridor of clarity, a silent tunnel where light can travel with little more than the stretching of space-time to contend with. But even in this emptiness, light is not entirely free. Quantum physics imposes its own texture on the vacuum. What we call empty space is not truly empty. It seethes with fleeting particles, virtual particles popping in and out of existence. These particles exist only for unimaginably small fractions of a second, but their presence affects the propagation of light in subtle ways. Though the effect is tiny, it means that even the purest void has a kind of quantum grain, a faint murmur beneath the silence. This quantum vacuum doesn't scatter photons, but it does define the rules under which light travels. And there's another influence: the curvature of space-time caused by the total mass of the universe. Even voids, seemingly empty, are shaped by the gravitational skeleton of the cosmos. Dark matter, though sparse within voids, still threads through and around them, contributing to the large-scale curvature of space. Photons follow this curvature, not freely in straight lines but along geodesics, the natural, straightest possible paths in a curved universe. These paths can be bent subtly by distant clusters or distorted by filaments at the edges of voids. Over billions of years, these slight bends accumulate. A photon's path may curve gently as it skirts the outskirts of a supercluster or passes through a region where dark matter is more concentrated. This phenomenon, known as weak gravitational lensing, changes the apparent shapes of galaxies when viewed from Earth. The distortions are minute, often requiring extremely precise measurements to detect, but they reveal the hidden presence of matter otherwise invisible. Even in emptiness, gravity leaves its fingerprint on light, yet the void remains the most transparent region in the cosmos. It is the place where light can express the pure consequence of expansion. Here, a photon becomes a time traveler. With nothing to hinder it, it crosses distances not in miles or kilometers, but in eons. A photon leaving a quasar 12 billion years ago may have passed through multiple voids, each one allowing it to drift unhindered, its story preserved on a wave stretched thin by the universe's quiet breathing. As it arrives at Earth, that photon tells us what the universe looked like when galaxies were young, when stars were first forming heavy elements, when black holes ignited jets that pierced the cosmos, all because the void allowed it to carry that ancient light like a sealed letter that no hand ever touched. If the cosmic void were filled with matter, our view of the universe would be radically limited. Distant galaxies would blur. The early universe would be hidden. The cosmic web would be harder to map. But because the void is so empty, it becomes a window, one of the clearest windows ever formed by nature. And as we explore this journey of light through emptiness, another question gathers at the edge of the darkness. If even light can cross the void so freely, then what invisible forces are shaping the emptiness itself, quietly influencing the galaxies that frame its borders? Part 7. The role of dark matter in shaping. Empty space. Dark matter does not shine, but it sculpts. Even the emptiest regions of the universe hold faint traces of this invisible mass, forming ghostly halos that guide the flow of galaxies. To understand why voids exist, we must look to dark matter's quiet architecture, which forms the skeleton upon which all cosmic structure rests. To imagine what dark matter does, you have to picture the universe not as a scatter of galaxies, but as a vast, invisible framework, an enormous 3D lattice of mass that emits no light, yet shapes everything we can see. Before the first stars formed, before galaxies spiraled into life, before the universe even cooled enough for atoms to exist, dark matter had already begun its silent work. It clumped, it gathered, it formed the first seeds of structure in a cosmos that was otherwise hot, smooth, and expanding. These early clumps, small concentrations of dark matter, acted like gravitational wells. As the universe cooled, normal matter began to flow toward them. Hydrogen and helium gas drifted inward, pulled gently by gravity. Over time, these invisible wells deepened and merged, forming larger halos. Inside these halos, galaxies were born, spinning disks, glowing clusters, and vast spirals of stars. But between these halos, something else was forming too. Regions where dark matter was scarce, where gravity was weaker, and where matter had little reason to gather. These were the first voids. Even now, billions of years later, every cosmic void owes its emptiness to the architecture established by dark matter in the universe's earliest moments. Where the dark matter density was low, ordinary matter avoided those regions. As matter moved toward denser regions, the emptier areas became even emptier. Voids expanded, deepened, and stretched like pockets of silence between the growing filaments of the cosmic web. It is easy to imagine dark matter shaping the bright parts of the cosmos, galaxies, clusters, glowing arcs of stars, but its influence on emptiness is just as profound. A void is not simply the absence of matter, it is the result of mass flowing away from regions that lacked enough dark matter to anchor structure. In this sense, voids are sculpted not by what they contain, but by what they do not. If we could see dark matter directly, the universe would look like a ghostly honeycomb. Filaments, long tendrils of invisible mass, would glow faintly, connecting dense clusters like threads of silk. At the intersections of these filaments, great knots of dark matter would shine brightest, marking the centers of galaxy clusters. And between these glowing nodes and strands, you would see the true voids, vast, gently curved hollows where the dark matter density dips lowest, forming the cosmic equivalent of valleys between mountains. These valleys create gravitational landscapes that guide how galaxies move. A galaxy near the edge of a void feels a subtle tug toward the denser regions outside it, like a pebble near the edge of a shallow basin. Over billions of years, galaxies drift outward toward filaments. Their motion is not chaotic, nor random, but guided by the shape of dark matter's invisible hills and hollows. The void empties itself further, not through any active force pushing matter out, but through the passive guidance of cosmic topography shaped by dark matter's early distribution. Dark matter's influence extends far beyond the visible edges of galaxies. Each galaxy sits inside a halo of dark matter that reaches far into the void, sometimes hundreds of thousands of light years beyond the last star. These halos are not smooth. They ripple with subtle variations, small clumps, and tidal distortions from past interactions. In void galaxies, these halos are especially pristine. With few neighboring galaxies to disturb them, their shapes provide valuable clues about how dark matter organizes itself on cosmic scales. Some halos are nearly spherical, others stretch into ellipsoids. Some contain subhalos, smaller pockets of dark matter that would, in denser environments, host dwarf galaxies. In voids, these subhalos may never gather enough normal matter to form stars. They remain invisible, silent, drifting through emptiness like dark islands without lighthouses. Yet these halos still influence their surroundings. Their gravity alters the motion of nearby particles, changes the paths of photons, and subtly shapes the structure of the void. Even in near-perfect emptiness, dark matter never truly disappears. Its presence, faint as it may be, ensures that no region of space is entirely without gravitational texture. One of the most fascinating consequences of dark matter's influence is how voids expand. In denser regions, dark matter clumps slow cosmic expansion by anchoring matter together. But in voids, where dark matter density is low, expansion proceeds more easily. Space stretches more freely here. The result is that voids grow faster than other parts of the universe. They balloon outward, pushing galaxies toward filaments, sharpening the contrast between full and empty. This accelerated expansion makes voids some of the most evolving structures in the cosmos. While galaxy clusters grow through mergers and accretion, voids grow by lightening, by losing whatever little matter they once had. Dark matter sets the boundaries, but cosmic expansion deepens the hollows. Dark matter also influences the temperature of voids. In regions with dense dark matter, gas is heated by gravitational collapse, but in voids where gravity is weak, gas cools easily. Hot gas drifts outward into emptier regions, losing energy as it expands. Dark matter's faint pull determines how this gas moves, how quickly it cools, and how long it remains in these quiet environments. The temperature of a void is not just a consequence of emptiness, it's a consequence of dark matter shaping how energy spreads. Even light responds to dark matter's architecture. When photons pass near filaments or clusters, they experience weak gravitational lensing, subtle distortions that stretch or shear their path. In voids, the opposite happens. Light passing through a void experiences a slight gravitational underdensity, allowing it to travel marginally faster than in denser regions. This effect is tiny, almost impossible to detect for a single photon, but statistically measurable across millions of observations. It forms a quiet imprint, a signature of dark matter's absence rather than its presence. And then, there is the cosmic web itself. Without dark matter, the universe would not have the intricate structure we see today. Galaxies would not gather into filaments, clusters would not form at their intersections, voids would not hollow themselves out into vast, graceful shapes. Dark matter is the architect not only of matter, but of emptiness. It defines the scaffolding on which cosmic evolution takes place. In the largest voids, the Boötes void, the Eridanus supervoid, dark matter density is exceptionally low. These regions stretch hundreds of millions of light-years across, containing only a handful of galaxies. Their shapes reflect the earliest ripples in the universe's matter distribution. They are remnants of ancient fluctuations magnified by time, their emptiness a quiet record of how dark matter arranged itself when the universe was young. And as we contemplate dark matter's silent role in shaping emptiness, another question begins to form gently at the edge of thought. If dark matter sculpts the voids, then how do those voids continue to grow, stretch and deepen as the universe expands toward its far future? Part 8. Why cosmic voids grow larger. Over time. As the universe expands, the dense regions grow denser and the empty regions grow emptier. Galaxies migrate toward clusters, leaving behind ever wider pockets of space. This natural sorting process, driven by gravity and expansion, means that voids are not static. They are evolving, stretching like slow cosmic tides. To understand why voids grow, we must return to the universe's earliest years, a time when matter was young, the cosmic web was only beginning to form, and the differences between dense and empty regions were barely perceptible. Back then, the distribution of matter across the cosmos was astonishingly smooth. Tiny fluctuations, mere ripples in density, were the only hints of future structure. In those slightly denser regions, gravity began its patient work, pulling matter inward. But in the slightly emptier regions, something else happened. Gravity's pull was weaker. Matter was less inclined to move inward, so it drifted gently toward the surrounding hills of mass instead. This contrast, the natural preference for matter to move from emptier regions toward denser ones, is what began the first voids. Gravity does not push matter out of voids. It simply pulls matter into the places where it is stronger. Over billions of years, this silent preference created a separation, areas of increasing density wrapped around regions of growing emptiness. As stars, gas, and dark matter streamed into forming filaments and clusters, the voids between them began to hollow out. What began as slight differences in density soon magnified into deep sweeping cavities, cosmic basins surrounded by bright walls of galaxies. But voids do not just grow because matter moves outward, they grow because the universe itself expands. Space is stretching everywhere, not just in crowded regions. But in voids, expansion has far less resistance. With almost no matter to slow it down, the void stretches more freely, like a drumskin pulled taut from the inside. Meanwhile, dense regions resist expansion. Their gravity binds stars, gas, and dark matter together, slowing the stretching of space locally. This difference creates a contrast in cosmic behavior. The universe expands fastest where there is almost nothing, and slowest where there is something. Over cosmic time, that difference becomes enormous. Imagine a balloon with thick patches and thin patches. When you inflate it, the thinner areas stretch more quickly. The voids in the cosmic web are those thin areas, regions where space grows outward with gentle ease. Each moment, a little more room appears between whatever particles happen to remain. It is not that matter is fleeing outward, but that space itself is forming between the particles. This is why voids can grow to be hundreds of millions of light-years across. Their size is not driven by a force pushing material away, but by a lack of gravitational anchors to hold that material in place. Yet the growth of voids is not just a story of expansion, it is also a story of migration. Galaxies move, not chaotically, but gently, following subtle gravitational gradients shaped by dark matter. Over time, galaxies near void edges feel a weak but persistent attraction toward surrounding filaments. They drift inward, drawn to denser, more massive regions. This movement is slow, measured in tens of millions of years, but steady enough that a void's interior empties further as galaxies depart. This migration makes voids more spherical over time. Initially, voids form in random shapes, molded by fluctuations in dark matter density. But as galaxies leave, voids tend toward roundness, relaxing into the shape that gravity naturally prefers when left alone. Some voids merge with others, creating even larger cavities, supervoids that span vast stretches of the cosmic web. These mergers are not violent, they happen quietly as empty regions bleed into one another across expanding space like bubbles merging in a rising tide. Another factor driving void growth is the cooling of the universe. In the early cosmos, hot gas permeated everything, filling voids more evenly. But as the universe aged and cooled, this gas lost energy, slowed, and drifted toward denser regions. What remained inside voids grew thinner and thinner. Some models suggest that voids may eventually become so empty that even dark matter within them grows scarce, swept outward toward the edges. In such scenarios, the centers of voids become some of the coldest, loneliest regions of all, so empty that not even gravity has much left to work with. But perhaps the most profound contributor to void growth is dark energy, the mysterious driver of cosmic acceleration. As the universe expands, dark energy's influence grows stronger relative to gravity. It acts uniformly, pushing all of space apart. In dense regions, gravity counteracts this push, but in voids where gravity is weakest, dark energy's pull is more effective. This imbalance deepens the emptiness, accelerating the outward motion of void boundaries. Over billions of years, this creates a dramatic effect. Voids expand faster than any other part of the universe. As dark energy shapes the universe's large-scale fate, voids become its quiet masterpieces, vast sculptures carved not by force, but by a cosmic absence of forces. Galaxies at the edges of voids begin to experience the combined effect of gravitational attraction toward clusters and the outward stretch of expansion behind them. They feel pulled in one direction and gently pushed in another. Their trajectories curve, shaped by these competing influences. Some galaxies may even be ejected outward along filaments as voids expand behind them, an elegant reflection of how emptiness can drive motion. This ongoing growth of voids has profound consequences for the future of the cosmos. As voids enlarge, the cosmic web becomes more exaggerated, filaments narrow, clusters grow more massive, galaxies fall inward, merging and evolving more rapidly in dense regions. Meanwhile, the voids become vast deserts, with only a few lonely galaxies drifting inside them. In the distant future, as expansion continues, voids may dominate most of the observable universe. The cosmic web will thin, stretched gently by time until most structures lie at almost unimaginable distances from one another. A galaxy inside a void might someday become completely isolated, with no visible galaxies left for trillions of light years. The night sky would dim into near emptiness, its stars dwindling as cosmic acceleration pushes everything outward. This is not a violent fate. It is a quiet one, a slow deepening of silence across the cosmos, a gentle widening of gaps between the islands of matter. And yet, even as voids grow, their edges remain the birthplaces of structure. Galaxies form along filaments, clusters merge, dark matter continues, shaping gravitational pathways. The contrast between full and empty sharpens, like ink spreading across old parchment. Voids grow because they are the universe's natural basins, regions where gravity is weakest, expansion is strongest, and migration favors departure. They grow because matter moves from low to high density, leaving behind carefully sculpted hollows. They grow because dark energy accelerates expansion in places where nothing resists it. They grow simply because there is nothing to stop them. And as this silent expansion continues, a new question gathers at the frontier of emptiness. If voids grow by letting matter drift away, what happens to the galaxies that remain stranded inside them, scattered like embers in the vastness? Part 9. What lives inside a cosmic void? Despite their name, voids are not completely barren. A few lonely galaxies wander their depths, small, isolated systems forming stars slowly and quietly. These galaxies evolve differently from their crowded counterparts, shaped more by internal processes than by cosmic interactions. In a way, they are the introverts of the universe. To imagine life inside a cosmic void, you must picture an environment so empty that distances stop feeling real and time stops feeling urgent. A void is not simply a hollow region, it is a vast domain where galaxies drift like faint lanterns in an endless night. A single galaxy inside such a space may be separated from its nearest neighbor by tens of millions of light years. That distance is so great that, even traveling at the speed of light, a message would take longer to cross it than modern humans have existed. And yet, within this cathedral of silence, galaxies persist. These void galaxies, sometimes called void dwarfs or void spirals, are some of the most fascinating structures in the cosmos, precisely because they have evolved in near total solitude. Unlike galaxies in clusters, which are constantly tugged, stripped, heated, or collided, void galaxies lead gentle, almost undisturbed lives. They evolve through internal processes, the slow cooling of gas, the gradual birth of stars, the mild influence of their own dark matter halos. Their isolation gives them a kind of purity. They often contain fewer heavy elements than their cluster-bound cousins, because they have experienced fewer cycles of star formation and fewer infusion events from galactic mergers. In many ways, they are echoes of the early universe, preserving chemical signatures that in other places have been overwritten by cosmic activity. Studying them allows astronomers to glimpse what galaxies may have looked like billions of years ago. Most void galaxies are small, dwarf irregulars, or faint spirals. They tend to be blue in color, a sign that they are still forming stars, but doing so calmly and quietly. Without nearby galaxies to disturb their gas reservoirs, they can hold on to their star-forming material for far longer than galaxies in dense regions. Their evolution is slow, stretched across billions of years like a peaceful exhale. A void galaxy is shaped less by the universe around it and more by the universe within it. Its gas cools into pockets of star formation without being compressed by external forces. Its dark matter halo governs its rotation curve without being torn or stretched by tidal encounters. Its stars form from a kind of cosmic introspection, each generation emerging gently from the remains of the previous one. Yet, not all void galaxies are small or faint. Some voids contain striking oddities, surprising, isolated giants whose existence defies the typical patterns of cosmic structure. These galaxies, though rare, are enormous spirals with extended disks and pristine outer regions. They are thought to grow through slow, steady accretion of cold gas, drawn in from the faint tendrils of the cosmic web that permeate even the emptiest regions. With nothing to disrupt them, their disks can become remarkably symmetrical and stable, forming near-perfect spirals that stand alone in the darkness. Interestingly, some void galaxies reveal evidence of dormant black holes at their centers. These black holes, unlike the active ones in dense regions, lack a ready supply of gas to feed on. They sit quietly, influencing the motion of nearby stars, but rarely erupting into the bright flares associated with feeding events. Even the most powerful forces in the universe become subdued inside the void. One of the most intriguing features of void environments is how slowly star formation proceeds. In clusters, galaxy collisions trigger rapid bursts of star creation, but in voids, such interactions are extremely rare. Without external triggers, star formation follows a much slower rhythm. Clouds of hydrogen gather, cool, and condense at their own pace. A star may take hundreds of millions of years to form, a patient, gradual process shaped by the calmness of its surroundings. This slow pace gives void galaxies a distinctive appearance. Their light profiles are softer, their distributions more diffuse, their stars are spread more evenly, as if the galaxy never experienced the violent encounters that often reshape galaxies in crowded environments. Viewed from afar, a void galaxy might look like a fragile swirl, delicate and slightly underdeveloped, but beautifully unspoiled. But perhaps the most mysterious inhabitants of voids are the galaxies that never formed at all. These are dark matter halos that, for one reason or another, never accumulated enough ordinary matter to ignite star formation. They drift invisibly through the void, detectable only by their gravitational influence. These shadow galaxies, sometimes poetically called dark galaxies, may be numerous. Some cosmologists believe they could outnumber luminous void galaxies by significant margins. Their presence suggests that even where visible matter is scarce, the cosmic web's hidden scaffolding remains intact. There are also traces of gas inside voids, thin, wispy filaments of hydrogen that stretch across vast distances. These filaments are faint, almost ghost-like, but they form the subtle bridges connecting void galaxies to the larger cosmic structure. They act as slow conduits for raw material, allowing some void galaxies to maintain star formation for billions of years longer than galaxies surrounded by violent neighbors. These gas streams are so tenuous that a cubic kilometer might hold only a handful of atoms. Yet, over immense spans of time, they feed galaxies just enough to sustain gentle star birth. If dense clusters are like bustling cities filled with interactions and collisions, the voids are like remote oases, quiet, self-sufficient, far removed from the pressures of cosmic society. Inside the deepest voids, the absence of external radiation also plays a role. Without the intense ultraviolet backgrounds found near active galaxies or quasars, void galaxies can retain their cold gas more effectively. This isolation shields them from the harsh radiation fields that strip gas from galaxies in crowded regions. Protected by solitude, they become long-lived reservoirs of primordial hydrogen. Voids also contain cosmic relics, photons from the cosmic microwave background, drifting through nearly perfect transparency. These photons carry information about the early universe, unscattered and unabsorbed, making voids some of the cleanest windows into the ancient cosmos. They pass silently through whatever little matter remains, forever altered only by the gentle stretching of space. In some voids, astronomers have detected faint groups of galaxies, tiny associations of 2 or 3 galaxies interacting slowly, almost hesitantly. Unlike the rapid, violent mergers seen in clusters, void group mergers are graceful and unhurried. Gravity gently draws them together over billions of years. When they finally merge, the event is quiet compared to the chaotic collisions in dense regions. The resulting galaxy may be smoother, less disturbed, and more symmetric than its cluster-born counterparts. Looking deeper, there are theoretical predictions of even stranger inhabitants. Rogue stars ejected from galaxies, faint globular clusters that drift through voids, and even planetary systems unbound from galaxies entirely. These are speculative, but not impossible. A void's emptiness is not a barrier. It is simply a canvas across which remnants of galactic evolution might drift for eons. The lives of void galaxies remind us that cosmic evolution is not uniform. It is shaped by environment. In the great emptiness, galaxies grow quietly, patiently, without interruption. Their existence highlights the subtle balance between gravity, isolation, and time. They show us what the universe looks like when left alone, how structure unfolds when allowed to evolve without violence. And as we drift deeper into this solitude, another question gently forms. If void galaxies evolve so differently from their crowded cousins, how does cosmic expansion shape the very fabric of the emptiness they inhabit? Part 10. How cosmic expansion creates more nothingness. The expansion of the universe does not simply push galaxies apart. It increases the total amount of emptiness. Every second, new space appears, fresh volume, fresh vacuum, fresh nothingness for galaxies to drift through. Understanding the void means understanding the expansion that continually builds it. To grasp how expansion creates more emptiness, we must begin with a quiet but profound truth. The universe is not expanding into anything. Space isn't pushing into a surrounding emptiness. Instead, space itself is stretching, unfolding from within. Every cubic centimeter of the cosmos grows, as though the universe is gently inflating from the inside out. And as it does, the emptiest regions, cosmic voids, feel the expansion most strongly. Imagine the universe as a soft grid of points connected by elastic lines. Each point marks the position of a galaxy or a particle, or even nothing at all. When the grid stretches, the distances between points increase. New space emerges as the lines lengthen. The points do not move through the grid, they are carried by it. In the densest regions, gravity pushes back against the stretching. But in the emptiest regions, nothing resists. Each moment, the grid expands more freely in the voids, giving rise to more space, more volume, more quiet. This is why cosmic voids grow faster than galaxy clusters. In regions where matter is abundant, gravity holds everything together. It slows the stretching of space. But inside a void, where mass is sparse, gravity has very little to counteract expansion. Space stretches almost unopposed and the voids balloon outward. Over billions of years, this difference becomes dramatic. Clusters condense, while voids swell. But the expansion of the universe does more than enlarge the spaces between galaxies. It creates new space, new emptiness, new nothingness. Where does this new emptiness come from? It comes from the fabric of space-time itself. As the universe expands, space-time stretches. This stretching does not dilute the emptiness, it makes more emptiness. For every second of cosmic time, more void appears. The universe is not just growing larger, it is producing more nothing, and this newly created emptiness behaves differently from the emptiness that came before. It inherits the uniform coldness of the cosmic background, the absence of matter, the quiet of space where particles rarely meet. It expands seamlessly into the older regions of vacuum, blending into the cosmic architecture like a calm tide merging with deeper water. The expansion is not uniform everywhere. Dense regions resist while empty regions yield. Imagine stretching a sheet of rubber where some areas are weighted down by stones. The sheet stretches most easily where there are no stones, the empty patches. This is what happens in the universe. Void regions act like flexible fabric, allowing expansion to flow more freely. Clusters act like anchors, resisting the stretch. This difference is so fundamental that cosmologists use voids as probes to measure the nature of expansion. The rate at which voids grow reveals details about dark energy and the overall geometry of the cosmos. By mapping how emptiness expands, scientists can infer the invisible forces shaping the universe's fate. But expansion does more than create new emptiness, it also isolates galaxies. As voids grow, galaxies drift farther apart not because they are moving through space, but because new space forms between them. Their separation increases even if they remain stationary relative to their local environment. This is why galaxies seem to recede from each other faster the farther away they are. More expanding space lies between them. This has a curious consequence. The more emptiness the universe creates, the more dominant the voids become. Filaments thin, clusters grow relatively denser, but occupy smaller fractions of the cosmos. The cosmic web becomes more exaggerated. Matter gathers into narrow strands, while voids break open like growing bubbles between them. In the distant past, voids were smaller. The universe was more uniformly filled with matter. As expansion continued, it magnified initial differences, pushing matter into filaments and widening the gaps. Voids merged, forming supervoids, vast cavities that today stretch across hundreds of millions of light years. As these enormous hollows grew, they shaped the gravitational flow of the universe, influencing how galaxies drift and how large-scale structures evolve. Expansion also affects the temperature of space. As the universe stretches, particles grow farther apart. Their interactions become rarer. Energy spreads out. The cosmic microwave background cools steadily, shifting to longer and longer wavelengths. This cooling reflects the increasing emptiness of the universe. As particles separate, they share less energy. Heat becomes harder to maintain. Emptiness deepens, not just spatially, but thermally. In a strange way, expansion is a process that creates silence. It dims the intensity of radiation. It stretches the fabric of time itself. It isolates galaxies into quieter neighborhoods. The void becomes a sanctuary of solitude carved by the universe's own breath. Dark energy plays a central role in this process. As the universe expands, the effect of dark energy grows stronger relative to gravity. It accelerates expansion, especially in the emptiest regions. This means voids grow faster now than they did billions of years ago. The cosmic acceleration enhances their expansion, making them some of the most dynamic structures in the modern universe, despite their apparent stillness. Some cosmologists predict that voids will someday dominate the observable universe. As galactic clusters shrink relative to the vastness around them, the cosmic web may become so stretched that connectivity between filaments weakens. Galaxies may become islands in a sea of expanding space, each cluster isolated by billions of light-years of void. In that far future, the scale of emptiness will be difficult for any civilization to comprehend. The night sky will thin out. Distant galaxies will fade beyond the cosmic horizon, receding faster than light due to space-time expansion. Eventually, all but the nearest galaxies may disappear from view entirely. The universe will grow quieter, softer, emptier, as expansion generates more nothingness with every heartbeat of cosmic time. Yet, even then, the essence of structure will remain. Voids will continue to deepen, filaments will continue to narrow, and clusters will hold on to their stars as gravity resists isolation. Expansion will not erase everything. It will simply stretch the fabric around what remains. This interplay between gravity and expansion is what shapes cosmic evolution. Gravity gathers matter into the luminous structures we admire. Expansion ever so gently pulls those structures apart, creating the stage on which the cosmic story unfolds. Voids grow because gravity fails to resist expansion in places where matter is sparse. They grow because every new moment of cosmic history adds fresh emptiness to the universe. In the grand scale of things, voids are the universe's most honest expression of expansion. They are the places where space is free to stretch, where the cosmos breathes most openly, and where the quietest truths of existence reveal themselves. And as we drift through this steadily growing oceans of nothingness, a new question rises. If expansion writes the emptiness, then what governs the delicate whispers of gravity that still exist within it? Part 11. Why gravity feels weak in the vast expanse. In the cosmic void, gravity thins out. With so little mass, its pull fades into subtle gradients across unimaginable distances. A galaxy drifting through this emptiness is influenced by forces so faint they take billions of years to matter. Here, gravity becomes less a tug and more a suggestion. To understand why gravity behaves so differently inside a void, we first have to reconsider what gravity truly is. We often imagine it as a force, something that pulls, something that acts like a tether between objects. But in the deeper language of the universe, gravity is not a force at all. It is the curvature of space-time itself. Mass bends the geometry of the universe, and objects move along the contours carved by that curvature. Where mass is abundant, space-time is deeply curved. Where mass is scarce, space-time becomes shallow, open, and quiet. Voids sit at the quietest ends of these cosmic contours. In a galaxy cluster, gravity is a roaring presence. Hundreds or thousands of galaxies orbit a common center, bound tightly by the massive concentration of dark matter. The space-time there is steep, like a deep gravitational valley. A galaxy entering such a region feels the pull immediately, as if falling down a cosmic hillside. But inside a void, the curvature is almost flat. There's little matter to warp space-time. The landscape becomes nearly level, like a vast open plain stretching in every direction. A galaxy in this environment is not pulled strongly anywhere. It drifts, not because something pushes it, but because there's nothing to stop it. The dominant feature of the void is not gravity. It is the absence of gravity. This lack of mass does not mean gravity disappears entirely. Even in the emptiest voids, the distant universe exerts a faint influence. Gravity is infinite in reach, but finite in strength. A galaxy inside a void still feels the gravitational pull of nearby filaments, clusters, and dark matter halos. But these pulls are subtle whispers, their effects building up only across cosmic timescales. Imagine a marble resting on a tabletop. The table is not perfectly flat. It has slight undulations, but the slopes are so gentle that the marble barely moves. Over hours or days, it might drift a little, but only if nudged by the faintest tilt. This is how galaxies behave inside voids. They respond to distant masses as if sliding slowly across a nearly level surface, following gradients so shallow that measurable movement takes billions of years. This slow drift reveals something fundamental. Gravity inside a void is not absent, but diffuse. It operates across vast distances, its influence stretched thin like a long, soft tether. In dense spaces, gravity dictates motion clearly and immediately. In a void, gravity becomes philosophical, a slow, patient guide rather than a commanding force. Dark matter plays an essential role here. Even voids contain traces of dark matter, though far less than average. Without dark matter's invisible mass, galaxies would float truly untethered. But because dark matter permeates the universe, even the emptiest regions have some gravitational texture. That texture is faint, like the tiniest ripples in an otherwise flat lake, but it is enough to influence motion over aeons. These faint gradients explain why void galaxies still migrate toward filaments. From a human perspective, the pull is imperceptibly weak, but gravity has infinite patience. Over billions of years, even the gentlest slope can coax a galaxy along. This slow march shapes the evolution of voids themselves, emptying their centers and sharpening their boundaries. Another reason gravity feels weak inside voids is that there is almost nothing to counterbalance cosmic expansion. In crowded regions, gravity battles expansion fiercely. Galaxies and clusters do not drift apart significantly because gravity is strong enough to bind them. But inside a void, there is no such anchor. The expansion of space dominates. It stretches the void like a quiet breath pushing outward, overpowering the faint gravitational pull of distant structures. This competition between gravity and expansion defines the behavior of void galaxies. Gravity tugs weakly toward the nearest mass, while expansion gently stretches the space around them. The result is a dance between two competing influences, one slow, one steady, neither of which is strong enough to overwhelm the other entirely. Galaxies follow trajectories shaped by both curvature and expansion, moving along paths that are not straight lines, but gentle arcs molded by invisible forces. The weakness of gravity in voids also affects the formation of new structures. In denser regions, small fluctuations in density collapse rapidly under their own gravity, forming new galaxies or star clusters. But in voids, the opposite happens. The lack of mass prevents collapse. Gas clouds remain too diffuse to coalesce. Dark matter halos accumulate slowly, if at all. This is why voids remain empty. They cannot easily form new structure because gravity is simply too weak there to initiate collapse. Even the temperature of voids reflects gravity's weakness. In dense regions, gravitational collapse heats gas, creating shock waves and igniting star formation. But in voids, gas rarely feels such compression. Instead, it expands and cools. Gravity cannot gather it efficiently. As a result, the void becomes one of the coldest environments in the universe. Its thermal history shaped more by expansion than by gravitational influence. Yet despite its faintness, gravity inside voids leaves a measurable signature. One of the subtler effects is gravitational potential energy. Light passing through a void experiences a slight blue shift as it enters the shallow gravitational potential and a corresponding red shift as it leaves. The net effect is a tiny stretching of light, a delicate imprint known as the integrated Sachs-Wolf effect. This effect reveals that even emptiness has gravitational shape, a shallow bowl carved by sparse dark matter. On cosmic scales, void gravity helps guide the flow of entire filaments. The surrounding walls of matter create a subtle outward push, encouraging voids to expand. Meanwhile, the faint pull of surrounding masses molds void boundaries into roughly spherical shapes. Even emptiness is sculpted by gravity, not by the presence of mass, but by the absence of it. One of the most intriguing consequences of weak gravity in voids is how it affects time. In regions with deep gravitational wells, time runs slightly slower, a consequence of general relativity. But in voids, where the gravitational potential is shallow, time runs ever so slightly faster. This difference is minuscule, almost impossible to notice, yet it reflects the profound truth that gravity shapes not only motion in space, but time itself. A clock drifting through a void ticks a tiny bit quicker than one in a cluster. In these vast expanses, gravity becomes a kind of cosmic background music, soft, gentle, and unwavering. It provides direction without urgency, influence without force. Its weakness is not a flaw, but a feature, allowing voids to remain empty, allowing galaxies to drift freely, allowing the universe to evolve into the web-like structure we observe. As we contemplate this gentle version of gravity, so unlike the strong, binding force that shapes stars and planets, we arrive naturally at a deeper question. If gravity is so faint in these regions, what other subtle energies or relics still inhabit the void, quietly filling even the emptiest spaces with the faint echoes of the universe's birth? Part 12. How black holes influence the nothingness around them. Even in emptiness, black holes leave signatures. Their gravitational influence extends far beyond the galaxies that host them, bending the paths of particles, shaping the orbits of stars, and subtly weaving the surrounding void. To understand the nature of nothing, we must also understand the creatures that inhabit its edges. Black holes are often imagined as violent objects, cosmic predators devouring anything that comes too close. But in reality, much of their influence is quieter, subtler, and more architectural. Their presence shapes the curvature of space-time on scales far larger than their event horizons. In the deepest stretches of the cosmic void, where matter is sparse and interactions are rare, even a distant black hole can alter the flow of particles and the motion of galaxies. To understand this influence, imagine a black hole embedded in a galaxy drifting near the edge of a void. The galaxy itself may be faint, isolated, and evolving slowly, but its central black hole, whether millions or billions of times the mass of the Sun, remains a significant sculptor of the space around it. Its gravitational pull extends into the void like an invisible hand, shaping local curvature even where no matter exists to respond. Gravity does not end where matter ends. It extends infinitely, thinning with distance but never reaching zero. A black hole, even in a lonely galaxy, leaves a gravitational fingerprint imprinted onto the emptiness. In an environment as quiet as a void, that faint influence becomes more noticeable over cosmic time. With almost no competing forces, the black hole's gravitational shape becomes a defining feature of the empty region around it. One of the most surprising aspects of black holes in void environments is how they alter the trajectories of lone particles drifting through the emptiness. A stray proton or dust grain wandering across millions of light years might eventually pass through the outskirts of a black hole's gravitational well. Even at immense distances, the well is deep enough to pull the particle ever so slightly, bending its path. This tiny change in direction becomes magnified over millions of years, turning an almost straight trajectory into a graceful arc. The void may seem empty, but these arcs reveal the hidden mass embedded at its edges. Galaxies within voids also feel this influence. Their orbits are shaped partly by the void's overall geometry and partly by the black holes at their centers. The presence of a supermassive black hole stabilizes a galaxy's inner regions, anchoring its rotation, maintaining its structure against the slow pull of surrounding filaments. In dense environments, external gravitational forces can distort galaxies dramatically, but inside voids, where gravitational competition is low, a black hole's stabilizing influence becomes even more pronounced. It acts as a steady keel guiding the ship-like galaxy through a vast, calm sea. Black holes also influence how void galaxies evolve. In dense clusters, black holes often feed actively, consuming gas and releasing powerful jets of energy. These jets stir their host galaxies, heat surrounding gas, and sometimes suppress star formation. But in voids, there is little gas to feed on. Void galaxies are quiet environments. Their central black holes often lie dormant for billions of years, shining only faintly or not at all. Yet, even a dormant black hole shapes the galaxy around it. Its presence affects the orbits of stars, guiding them into stable paths. It organizes the central bulge, influences the symmetry of the galactic disk, and stores enormous amounts of gravitational potential energy. The black hole may be silent, but its influence is foundational. It sets the rules by which the galaxy maintains coherence in an environment where external perturbations are minimal. Some void galaxies contain surprisingly large black holes for their size. This has puzzled astronomers who expected smaller galaxies to host proportionally smaller black holes. Instead, some of these galaxies appear to have grown their black holes more efficiently, perhaps because their isolation prevented disruptive events that might otherwise fling matter outward. In void conditions, with gentle inflow of cold gas and fewer mergers, a black hole can grow slowly but steadily, accumulating mass without turmoil. These overgrown black holes provide clues to how supermassive black holes may have formed in the early universe. Black holes may also influence the shape of voids themselves. On the largest scales, void boundaries are dominated by filaments of dark matter, but on local scales, the gravitational pull of galaxies and their central black holes can subtly adjust the interior geometry of a void. A black hole's long-range gravitational field slightly alters the distribution of gas and dark matter in its vicinity. Over billions of years, these small changes accumulate, shaping small pockets of curvature inside the broader emptiness. In some scenarios, black holes might even eject stars or gas into voids. When two black holes merge, or when a black hole interacts dynamically with another massive object, gravitational recoil can launch stars outward at incredible speeds. Some of these stars could be flung into the voids, becoming lonely wanderers traveling without a host galaxy. Though such hypervelocity stars are rare, they add a subtle richness to the void's population, traces of galactic drama cast into vast silence. Black holes also influence the radiation environment of voids. A dormant black hole emits almost no light, but an active black hole, even far from a void center, produces powerful jets and high-energy radiation capable of crossing enormous distances. In an empty region with few obstacles, these emissions travel cleanly, illuminating faint gas or heating tiny pockets of intergalactic material. The void might seem unaffected, but the black hole's light gently warms the thin gas that remains, a reminder that even emptiness can be touched by distant energy. Yet the deepest influence black holes exert on voids is conceptual. They remind us that emptiness is never truly empty. Even in the vastest regions of the universe, geometry has shape, energy leaves traces, and gravity draws invisible patterns across the dark. A black hole's presence reveals the subtle structure underlying even the emptiest volumes of space. It is tempting to imagine a void as a place without story, a place where nothing happens, nothing moves, nothing grows. But when we consider the influence of black holes, we see that voids are dynamic. They are sculpted by the galaxies around them, and those galaxies are shaped by the black holes within them. Even silence has structure. Even emptiness has architecture. At the furthest edges of a void, where galaxies thin into faint whispers and darkness stretches uninterrupted, a black hole's influence might be indistinguishable from the curvature of the universe itself. And yet, it is there, subtle, patient, gravitationally persistent. This delicate influence leads us gently toward a deeper question. If black holes shape the emptiness around them, what fills that emptiness with the faint glow of ancient radiation, echoes that travel freely through these vast domains of nothingness? Part 13. the quiet radiation filling every empty space. Even the darkest void is not completely dark. It glows faintly with relic radiation from the Big Bang, the cosmic microwave background stretching across all of space like a ghostly afterglow. This radiation whispers the universe's earliest memories, passing freely through regions where matter is nearly absent. To understand the quiet radiance inside a cosmic void, imagine turning off every star, every galaxy, every quasar, every glowing cluster. Imagine removing every atom, every dust grain, every wisp of gas. What remains is not true darkness. Instead, a soft, ancient light continues to wash through the emptiness, a radiation so gentle and cold that it can only be felt by sensitive instruments. Yet it fills every corner of the cosmos with a faint, even glow. This glow is the cosmic microwave background, the oldest light in the universe. It comes from a time when the cosmos was young, just 380,000 years after the Big Bang, when the universe had cooled enough for light to move freely, for the first time. Before that moment, the cosmos was a dense fog of particles, opaque and chaotic. But when the fog cleared, photons were released, free to travel across billions of years. Those photons are still moving today, and they pass undisturbed through the deepest voids. Inside a void, where there's almost nothing to scatter or absorb them, this ancient light travels with remarkable clarity. The emptiness becomes a perfect medium, a quiet hallway through which the earliest memories of the universe continue their endless journey. The cosmic microwave background, CMB, is not bright in any ordinary sense. It does not illuminate galaxies or cast shadows. Instead, it forms a uniform, omnipresent backdrop. Its temperature today is about 2.7 Kelvin, just a few degrees above absolute zero. But that temperature is a clue to its origin. It tells us how much the universe has expanded since these photons were first released. Long ago, this light was blisteringly hot like the surface of a star. Now it is stretched, cooled, and softened by cosmic expansion. In the voids, the CMB becomes particularly important. Since there is little else to interact with, it becomes a dominant form of energy in these empty regions. Each photon that crosses a void provides a whisper of the early cosmos, a quiet note in the long symphony of cosmic evolution. But the CMB is not the only radiation inhabiting emptiness. There is infrared glow from distant galaxies, traveling freely across vast distances. There is radio emission from ancient supernova remnants, stretched and cooled by expansion. There are stray photons from quasars, gamma-ray bursts, and long-dead stars. These photons wander the universe like faint embers drifting through the dark. Most never encounter a single particle for millions of years. There's also a sea of neutrinos, relics from the first seconds after the Big Bang. These particles move almost completely unimpeded, even in dense regions. In voids where matter is scarce, they flow even more freely. The neutrino background is far colder and harder to detect than the CMB, but it permeates every part of the universe. It fills the void not with light, but with silent motion, an ocean of nearly massless particles streaming endlessly. Then there is dark energy, which is not radiation, but still fills every cubic centimeter of space. Its influence is felt everywhere, but it becomes especially noticeable in voids, where nothing counters it. Dark energy accelerates expansion, deepening the emptiness and shaping the future of the void. Though not a form of light, it affects how all light travels, stretching wavelengths as space expands. But the most delicate interplay between voids and radiation involves the CMB itself. The CMB is nearly uniform, but not perfectly so. It has small temperature variations, tiny fluctuations that reflect density differences in the early universe. These fluctuations ultimately gave rise to galaxies, clusters, and voids. But they also reveal something else. When CMB photons travel through large voids today, they undergo subtle shifts. This effect is known as the integrated Sachs-Wolf effect. Because voids are underdense regions, their gravitational potential is shallower and evolves differently from dense regions. As CMB photons enter a void, they gain a tiny amount of energy by falling into the shallow gravitational well. But as they leave, the the universe has expanded just enough that the photons do not lose all the energy they gained. The result is a slight, measurable warming, a faint brightening of the CMB in the direction of large voids. This means voids leave fingerprints on the oldest light in the universe. Even though they contain almost nothing, they imprint their existence onto radiation that has traveled for nearly 14 billion years. In this way, emptiness becomes a collaborator in the story of cosmic light. It shapes the photons that pass through it, creating subtle clues that cosmologists use to measure expansion and study dark energy. Radiation inside voids also reveals how transparent these spaces are. In galaxy clusters, photons are scattered by hot gas, absorbed by dust, or deflected by magnetic fields. But inside voids, none of those barriers exist. The voids act as cosmic windows, regions where light can travel nearly unaltered across enormous distances. By observing light that has passed through voids, astronomers can measure expansion more cleanly, map dark matter more accurately, and analyze the CMB with greater precision. In this sense, voids are not just empty regions, they are laboratories, quiet rooms in which the universe reveals its faintest, most ancient signals. The softness of the CMB, the purity of infrared light, the clean arcs of radio waves, all of these provide information that would be hidden in denser environments. On longer timescales, radiation inside voids also changes. As the universe expands, wavelengths stretch, light cools, photons lose energy. Eventually, in the deep future, the CMB will cool so much that it becomes almost undetectable. The universe will drift into greater darkness, but even then, voids will remain bathed in the faintest glow of ancient photons, residual, stretched beyond usefulness, but still present. At an even deeper level, the radiation within voids teaches us something about the nature of emptiness itself. True vacuum is not a simple nothing. It has energy, it has structure. Quantum fields fluctuate even in the absence of matter or radiation. The void is alive with microscopic activity, oscillations in the quantum fields that underlie all forces and particles. This quantum vacuum fills space more thoroughly than the CMB, more uniformly than neutrinos, more consistently than dark energy. Though we cannot see it, the quantum vacuum is the most pervasive occupant of cosmic voids. It generates virtual particles that flicker into existence before annihilating. It defines the ground state of the universe's fields. It may even be the engine behind cosmic expansion. The radiation we observe inside voids is layered atop this deeper, more fundamental emptiness. So when we say that voids are filled with quiet radiation, we are saying that the universe carries its memories everywhere. Light from the Big Bang, ghost particles from the earliest seconds, echoes from distant stars, the pulse of quantum fields, all drifting through a silence so deep that even the faintest whisper endures. As we listen to these ancient echoes, a new question emerges gently at the edge of our quiet exploration. If voids are filled with the universe's oldest light, what do they reveal about the subtle structure of space-time itself, its hidden threads, its quiet curves, and the invisible scaffolding that shapes all cosmic emptiness? Part 14. Why Emptiness Helps. Galaxies form and evolve. Paradoxically, the universe needs emptiness to grow complexity. The voids between galaxies create pressure differences, gravitational gradients, and temperature gaps that help shape the cosmic web. Without these near-perfect vacuums, galaxies would not cluster, clusters would not merge, and the universe would lack the structure we see today. It is easy to imagine emptiness as a passive backdrop, a blank stage on which galaxies act out their luminous stories. But cosmic voids are not passive. They are active participants in shaping the universe. Their presence creates the contrasts and gradients that make structure formation possible. Without emptiness, there would be no filaments, no clusters, no galaxies spiraling in stately rotations. Everything would blend into a uniform haze. The richness of the cosmos, the intricate web of matter stretching across unimaginable distances, arises only because emptiness exists to define it. To see why, imagine the early universe. After the Big Bang, everything was astonishingly smooth, almost perfectly uniform. Tiny fluctuations in density, like faint ripples on a quiet ocean, were the only differences that existed. Over time, those slight variations grew. The slightly denser regions began to gather more matter. The slightly emptier regions lost matter to their surroundings. This process magnified the contrast, deepening the hollows and building up the hills. Without these hollows, the first embryonic voids, matter would have had nowhere to flow. Structure grew because emptiness expanded. Emptiness, in other words, created direction. When matter moved from underdense regions into overdense ones, gravity amplified the process. More matter meant stronger gravity. Stronger gravity attracted more matter. Meanwhile, the voids, growing emptier, offered less resistance. They became highways through which matter could flow, guiding the growth of filaments and the formation of the cosmic web. Even today, the gravitational gradients created by voids help shape how galaxies evolve. A galaxy near the edge of a void feels a gentle pull toward nearby filaments. Its trajectory is influenced not only by where matter exists, but by where it does not. The voids create an outward push, not through pressure, but through a lack of pull. With so little matter inside them, voids do not counterbalance the gravitational attraction of nearby structures. Instead, they allow galaxies to slide away from emptiness and toward denser regions. This silent, slow movement is one of the fundamental drivers of cosmic evolution. Another way emptiness shapes structure is through temperature differences. In dense regions, gas is hot, heated by gravitational collapse, supernova explosions, and black hole activity. But in voids, gas expands freely and cools. Over time, this contrast sharpens. Cold void gas can drift along filaments toward denser regions, sinking like chilled air sliding down a mountainside. When it arrives, it can fuel star formation, replenish galaxies, and feed supermassive black holes. The coldness of voids becomes a quiet engine that sustains the dynamic behavior of galaxies in more crowded environments. This is particularly important for galaxies located along filament boundaries. They benefit from both sides of cosmic architecture, the stability of the void and the density of the filament. Gas moves toward them from the cooler, emptier region, providing fresh material for star formation. Meanwhile, their gravitational interactions with nearby galaxies in the filament encourage mergers, spin changes, and bursts of starbirth. The contrast between emptiness and fullness becomes a source of creation. Emptiness also plays a crucial role in preventing the universe from collapsing too quickly. When the universe was young, gravity tried to pull everything inward, but the vast empty regions resisted collapse, not by pushing back, but by simply not providing the mass needed to strengthen gravitational wells everywhere at once. They acted as buffers, stretching the timeline of structure formation. This allowed galaxies time to cool, stabilize, and evolve gradually. If the universe had been denser overall, if voids had been smaller or fewer, gravity would have overwhelmed the cosmos early on. Everything might have collapsed into enormous chaotic clusters. Star formation would have been turbulent and short-lived. The delicate spirals and gentle dwarf galaxies we see today might never have formed. Emptiness gave galaxies room to breathe, to rotate, to grow without constant disruption. The presence of voids also influences the shape of the cosmic web itself. Filaments form not just because matter gathers, but because emptiness expands between them. As voids swell, they stretch the filaments taut, sharpening their outlines. Clusters gather at filament intersections because voids leave those intersections untouched by the draining flow of matter. In this way, the deepest structures of the universe are shaped by a balance between matter sinking into gravity and emptiness expanding outward. One of the more subtle ways emptiness helps galaxies evolve involves the concept of shear, a gravitational phenomenon in which different regions of space expand at different rates. Inside voids, expansion proceeds slightly faster than average. Along their edges, the expansion slows where matter is denser. This difference creates shear forces that stretch matter into long strands. These strands become filaments, the skeleton of the cosmic web. Without the contrasting stretch of void expansion, filaments would not form as neatly or extend as far. Shear also shapes individual galaxies. The direction of a galaxy's spin often aligns with the shear created by nearby voids. Large spirals may orient themselves along filament axes, their rotation influenced subtly by the empty regions on either side. Even the dance of stars inside a galaxy can be influenced by the quiet pull of nearby emptiness, encouraging symmetric patterns or stable disks. At even larger scales, voids enable colossal mergers between galaxy clusters. As voids expand, clusters are slowly pushed together along the filaments that connect them. The emptiness between them behaves like a gentle separating force, ensuring that collisions occur along preferred cosmic pathways. These mergers, some of the largest events in the universe, release incredible amounts of energy, heating gas to hundreds of millions of degrees, igniting shocks and creating vast arcs of hot plasma. All of these events rely on emptiness to set the stage. Emptiness also helps galaxies maintain long-term stability. In dense environments, galaxies interact constantly. These interactions can strip gas, distort shapes, and trigger violent starbursts. But galaxies near void edges experience fewer disruptions. They evolve more peacefully, preserving delicate structures that might otherwise be destroyed. Some of the most pristine disks we observe lie near void boundaries. Galaxies that have lived calm, uninterrupted lives, shaped more by internal evolution than by cosmic conflict. This peaceful evolution reveals another paradox. Emptiness can nurture complexity. Within void-adjacent galaxies, star formation proceeds slowly and steadily. Their chemical compositions remain unique, preserving signatures from earlier cosmic eras. Their shapes remain coherent, sometimes forming symmetrical spirals free from the distortions caused by neighboring galaxies. These galaxies become living records of cosmic history, their existence made possible by the sheltering effect of emptiness. The interplay between voids and galaxies even extends into the future. As cosmic expansion accelerates, voids will grow faster than ever. They will push galaxies further apart, deepening the contrast between structure and emptiness. Filaments may thin but remain intact, while clusters become isolated islands in a widening sea of nothingness. In that future universe, the influence of emptiness will become dominant. It will shape the long-term evolution of galaxies, determining which survive, which remain visible, and which fade forever beyond the cosmic horizon. In this sense, emptiness is not a void at all. It is a process, a sculptor, an architect of cosmic order. It is the quiet frame around the universe's grandest structures, giving them room to exist and grow. And as we follow this gentle story of contrast and creation, a final question begins to rise softly at the edge of thought. If emptiness helps shape everything we see, what does it reveal about the deepest human urge to find meaning in the spaces between things, in the quiet, the stillness, and the vastness that holds the universe together? Part 15. How the void reveals the fate of the universe. If we look closely at the emptiest spaces of all, we find clues about the universe's future. Cosmologists study voids to understand dark energy, cosmic acceleration, and the ultimate destiny of everything that exists. The nothingness between galaxies may hold the quiet answer to how the cosmos will end, not with noise, but with expansion into deeper silence. To understand why emptiness is the key to the universe's fate, we must first recognize that voids behave differently from the rest of the cosmos. In dense regions, clusters, filaments, and luminous webs of matter, gravity battles the expansion of space. Stars cling to galaxies, galaxies cling to clusters, and clusters cling to the cosmic web. These are places where gravity still dominates. But voids tell a different story. Inside them, gravity loses its foothold. Expansion becomes the leading force. Space stretches freely, unopposed, deepening the emptiness. Voids are where the universe reveals its truest behavior. Everywhere else, gravity obscures expansion by binding matter together. But in a void, expansion acts cleanly and transparently. The rate at which a void grows reflects the rate at which the entire universe expands. As voids swell, they amplify the effects of dark energy. the mysterious pressure that accelerates cosmic expansion. By studying how voids grow and how their boundaries move, cosmologists can infer the strength and nature of dark energy. It is as if the voids themselves are sensitive instruments, cosmic barometers measuring the universe's accelerating breadth. When astronomers map the distribution of galaxies, they find enormous cavities stretching across space, supervoids that span hundreds of millions of light years. These vast hollows serve as anchors for our understanding of cosmology. Their shapes, depths, and growth patterns reveal how the universe is changing over time. Some of the largest voids even appear slightly hotter in the cosmic microwave background because of the integrated Sachs-Wolf effect, a signature of dark energy's influence on passing photons. These subtle imprints allow cosmologists to measure acceleration directly. Studying voids is like reading the universe's long-term weather report, and that report shows one trend with absolute clarity. The voids are winning. Emptiness is spreading, structure is shrinking in cosmic proportion. In the early universe, voids were small, barely more than gentle hollows among denser regions. But over billions of years, expansion magnified the contrast. The dense regions grew denser as matter collapsed inward. The empty regions grew emptier as matter drained away. The cosmic web sharpened into its now familiar shape, filaments outlining gargantuan pockets of nothingness. Today, voids occupy the majority of the universe's volume, and as cosmic acceleration continues, they will grow even larger. In the far future, they may dominate nearly all observable space. Galaxies will become isolated islands, tiny sparks of structure drifting through a sea of expanding nothingness. This is the first clue the void gives us about the universe's fate. The future belongs to emptiness. Cosmic acceleration ensures that the fabric of space will continue to stretch. Filaments will thin, clusters will grow more distant. Eventually, galaxies not gravitationally bound to one another will drift beyond the cosmic horizon, their light stretched into invisibility. The night sky will empty out, not because stars are dying, but because expansion is carrying everything away faster than light can keep up. Voids show us this process already underway. Even now, galaxies near void edges are subtly being pulled outward by the effect of expansion. They drift away from emptiness, not because the void pushes them, but because the rest of the universe pulls more effectively. The void acts as a gravitational lowland, a region where expansion is unopposed. As dark energy grows more influential, this balance will tip further. The universe will stretch faster. The voids will deepen more quickly. Eventually, the large-scale structure of the cosmic web will begin to dissolve, not through destruction, but through separation. Gravity can hold together local systems, galaxies, galaxy clusters, galaxy groups, but not the broader web. Those larger bonds will slowly unravel as space expands between them. In the far future, tens to hundreds of billions of years from now, the cosmic web may appear as a faint, skeletal remnant. Only the most massive clusters will remain as visible structures. Everything else will be too distant, too redshifted, and too faint to detect. The voids, once background features, will become the dominant geography of the cosmos. This brings us to the second clue voids offer. Dark energy shapes destiny. Dark energy is not well understood, but voids give us a window into its behavior. In voids, dark energy's influence is clearest. Where matter is absent, dark energy acts freely. It stretches space with a consistent, accelerating pressure. By observing how voids respond to that pressure, cosmologists can infer whether dark energy is constant or evolving. If dark energy remains constant, as current observations suggest, the universe will continue, accelerating indefinitely. The voids will grow without bound. Over unimaginable timescales, every galaxy not gravitationally bound to another will drift into permanent isolation. Communication between distant regions will become impossible. The large-scale universe will fade into darkness and quiet. But if dark energy evolves over time, voids will reveal that too. If dark energy weakens, expansion may slow, allowing some structures to remain loosely connected. If dark energy strengthens, expansion could accelerate so rapidly that even galaxy clusters disintegrate, though current models do not support this extreme Big Rip scenario. Still, void boundaries would be the first places where such effects would become apparent. In this way, the voids serve as the cosmos's long-range forecast. Their behavior tells us whether the universe is headed toward eternal expansion or something more complex. A third clue voids offer is about the ultimate temperature of the universe. Inside a void, matter is sparse, so gas cannot heat easily. As space expands, particles become even more isolated. Their energy spreads out and temperature falls. Today's voids are already some of the coldest places in the cosmos. In the distant future, as expansion continues and radiation stretches into ever longer wavelengths, the voids will cool even further. Eventually, the cosmic microwave background will fade into almost nothing. Starlight will no longer travel between galaxies. Energy will become so diffuse that space approaches absolute zero. The voids reveal this future clearly. The universe is heading toward cold, quiet emptiness. And yet, there is a final, more philosophical clue the voids provide, one that connects the vastness of cosmic emptiness to our own sense of meaning. The universe does not vanish with a bang. It fades gently. It softens. It widens. Its future is not catastrophic, but quiet. The story of the cosmos ends not in fire or collapse, but in separation, in distance, in stillness. The voids teach us that endings can be subtle. Just as stars age gently, galaxies drift slowly, and expansion progresses imperceptibly, the universe's ending will be a gradual deepening of silence. Darkness will not be the enemy. It will be the natural consequence of time stretching outward. In the end, the voids, those vast, quiet oceans of almost nothing, will define everything. They will grow until they occupy nearly all of existence. The islands of matter will shrink to tiny, lonely specks in an infinite sea of calm. And as we contemplate this soft future written into the void, a final whisper of a question arises. If the universe ends in deepening quiet, what does that silence reveal about our place in this vast unfolding story? About the fleeting brightness of galaxies, the endurance of emptiness, and the meaning we find in the spaces between stars?